And we're back. Welcome back from the weekend. Today we're going to continue on, finish up our discussion on regression, but the focus of today will be on implementation of regression using Matlab. Before we begin, a reminder, the reading material is Learning from Data. It's on linear model regression from the 21 minutes and 39 seconds in the video. There's the URL. Click on that URL. It will bring you to the correct time in the video from which you should be watching. In addition, on the course Blackboard, I've posted a PDF from Princeton University on ordinary least squares linear regression. So that's going to be the reading for this module, in addition to this video, of course. So we talked about the regression problem, and instead of talking about the credit classification, approval or denial, we talked about the prediction or the output of the credit line. And so we have our vector of valued input, x1, x2, x3, up to and including xd, so in d dimensions. And each one of these corresponds to an attribute, some number of attributes, d many, which collectively describe a particular credit applicant. And so we also have our linear function, w, that's going to be our linear hypothesis. And this credit line approval system is going to output some number, some real valued quantity. And it just so happens this real valued quantity is culled from historical records in the bank or the lending organization. And that's going to be the ground truth label corresponding to the amount of credit each particular historical applicant has received from the financial institution. And so we talked about this idea of how you select the W. And we said we want to select the quote-unquote best hypothesis, final best hypothesis, G. And so here in this example, we have our historical data. And in this particular example, we have along the horizontal axis, we have the amount of student loans. And along the vertical axis here, we have the amount of credit assigned by the bank or given by the bank, or the size of the credit line. And so as you can imagine, the larger the student loans, the less disposable income or less income you have available to pay back the loan, and therefore you're at greater credit risk and you'll get a smaller amount of credit extended. And the smaller amount the student loans, you'll have more of your income available to pay back the credit from the bank, the credit line, and therefore your credit line will be larger. So here we have two inputs. We have X1, which is student loan, $23,000. So this applicant, the first applicant, has $23,000 student loan, and the amount of credit assigned, the size of the credit line is $14,000. And then the second person, X2, has, for example, $58,000 of student loan, and the associated amount of the credit line assigned by the bank is $6,000. And so here we have two examples of applicants, each one with a different amount of student loans, and each one therefore is assigned a different size for the credit line. And so as you can see, X2 is bigger than X1, and therefore X2's credit line size is smaller than X1's credit line size. And so we have a number of such points, and the idea then is to find the hypothesis, the linear hypothesis, the weight vector W, that best describes this. And this best describing, or this best linear hypothesis, is one that is in the so-called middle of the data. And so how do we measure this idea of middle of the data? Well, we look at the difference between what this hypothesis outputs for each credit applicant's input representation, and we compare that to the difference between what that ground truth is. So here, if we take the vertical component of each one of these data points, well, that's the ground truth amount of credit. And if we take the vertical component of that input from the hypothesis, linear hypothesis, well, that difference between ground truth and what the hypothesis outputs, we call that a residual. And so we look at all of the residuals, both the positive residuals and the negative residuals, and we sum them, but we care about the magnitude and not whether they're positive or negative. And so we came up with an expression for error, in particular in-sample error, which is the square, because we care about the magnitude of the difference between what the hypothesis outputs, h of xn, and what the ground truth label is, that real valued quantity, which is the size of the credit line from historical data, yn. So we take the magnitude of that difference, or square that difference, because we care about the magnitude, and we don't care so much about whether it's positive or negative. And we effectively sum them up and we take the average. And so here for the one feature model, it's one feature because there's only a single descriptor for each applicant, and that's similar to the example showed on the previous slide. And then in this example on the right-hand side, the right pane, we have two features, right? These two features, right, represent, for example, X1 could be the annual salary, and X2 could be the amount of students' loans, right? So for each one of these descriptors, each point rather, corresponds to a particular annual salary and a particular amount of student loans, and the corresponding Y value is the amount of the credit line, or the size of the credit line signed by the bank for each one of these historical data points, which are representations of each applicant information to the bank. Okay, so we have these two best hypotheses, and these best hypotheses, as we said, are those that minimize this average square of the residuals or in-sample error. So we set out then to minimize this expression for in-sample error over all of the historical data. Okay, and so we did a little bit of manipulation, expressed it in matrix vector algebra, computed the pseudo-inverse, and we came up with this algorithm for linear regression. And so you start out with your labeled instance pairs. And so here we have x1, y1. Now x1, if we were to look at x1 is a d-dimensional feature vector. So that would be the first customer, the first feature, the first customer, the second feature, up to and including the first customer, the D feature, representing a D-dimensional vector. And so we have big N, many customers in our historical data, and we're going to take each one of these vectors and we're going to augment it with an X naught. And so we're going to take this X1, and this is going to be the augmented version. And how do we augment it? Well, we insert a dummy variable X naught, and we also include all the original features. And this gives us a vector of size D plus 1, because we had D features for the original information culled from the application, and we had another feature for a total of D plus 1 dimensions for the augmented vector. And so we construct a design matrix, and there's our design matrix, X, and it's a design matrix. This is formed as a so-called row matrix. So row matrix is a matrix where each row is a vector, and each one of the vectors corresponding to the rows of our design matrix, which is the matrix of all of your data, is going to be one of these augmented feature vectors for these N many customer records. And so we have the augmented data occupying the rows, and because these vectors are assumed to be column vectors, we have the transpose in order to make them row vectors so that we can put them together in the form of this row matrix, our design matrix X. So this is our input data, and then we also take all of the ground truth targets. Now these targets, this Y1, that would be the credit line for customer number 1, first customer, and this would be the credit line for customer number big N. And so here we have the credit lines for each one of our N many customers, and these were ground truth historical records from the data. And so the goal then is we compute the pseudo-inverse, and this gives us an expression for W, which is just the pseudo-inverse of your design matrix, times Y, which is the column vector of target labels, and these are all real values. So each one of these is going to be an element of a set of real numbers. Okay, so let's move on to Matlab, as that's sort of the main focus of today, and we'll look at this this result in Matlab. Okay, so we are in Matlab, and we start out, we have a mortgage data file. This would be our historical records from the bank. I mean, certainly doesn't matter where it comes from. You could get this from a SQL query from a company database, but I just stored it from a CSV file, and it consists of 2 columns, one feature representing the annual salary, and the second column is the ground truth amount of the size of the credit line. And so this is going to be one feature in terms of the regression model, and that's going to be our independent variable, and then the second column is going to be our dependent variable. So we define this and this data file, and we're going to read this in. First, we're going to set a little bit of definitions, define variables for making plots more beautiful, because we want to scale things appropriately so that it looks nice. And then we're going to jump right into reading this mortgage data. So we do a CSV read of this mortgage data. And if we step over this and take a look at this data, well, we have 100 data points, and each row of this data file from CSV format, read it into a matrix. The first column is the amount of annual salary, and so we start out with $250 of annual salary, and the second column is going to be the amount of mortgage that's lent. So here that would correspond to $79,000 of mortgage, and so each row of this table read in from our historical records is going to represent, each row is going to represent a feature vector. And so this is a very simple feature vector, i.e. it's a one-dimensional feature vector, where the second column is our ground truth label, which is real value. Okay, so the first thing we do is we're going to take the first column. And when we take this first column, that's going to give us the features. And then we're going to take that second column. So then we're going to take that second column, and that second column is going to give us the set of ground truth labels, right? Those are going to be our YI values. So here, Excel data are the X values, the D-dimensional feature vectors, and here on line 52, that Y is the set of ground truth labels, which are real values. And these Y's are the dependent variables. So then let's continue on. We measure the size, and then we'll just, for good measure, we'll plot out what this looks like for our input data, historical records. So we'll give it some labels, and let's blow up this figure. And if we take a look at it, we'll see along the horizontal axis, we have annual salary. And so it goes from 0 up to 100,000. And then here on the vertical axis, we have the mortgage amount that was lent, and so it goes from 250 to as high as, it looks like 70,000 here. Okay, let's take a look at this. So if we go up here, we'll take a look here, 728,000. So our mortgage can go up pretty high, a couple $100,000, and our salary can go up to about $100,000. Okay, so this is our plot of our historical data, and let's continue on. The next thing we're going to do is we're going to, let me minimize that graph, that figure. We're going to initialize our dummy variables, our X naughts, right? Because we need to augment each one of our 100 many feature vectors, and these feature vectors just happen to be one-dimensional, right? Very simple features. A single feature, which is the annual salary, describing each customer. All right, so we're going to build this X0 vector, and we're going to add it 1 to it to make it all 1. So we start out with zeros and we add 1, so we have this X0 as all 1s. And now you notice here we have an X0 for each one of these 100 many vectors for our input. And so we're going to basically paste on this column vector of X naughts onto that matrix of all of our data. And so here I've included in the comments some description, and we're essentially constructing our design matrix by including our X naught as the first column, and then we're filling in all the other columns, the second through the D plus first column, using each one of these row vectors from our data set that we got from the CSV file. So this is exactly what we're doing here. And in Matlab notation, we're constructing a new matrix, big X, our design matrix. The first column is going to be the X naught, and then the second through the D plus first columns are going to be each one of those vectors that we got from the data set. Okay, so we build our design matrix, and that's going to be our X as we discussed in our regression algorithm. So the next step now is we're going to compute our X transpose, because that's what we needed for our pseudo inverse. If we go back to our presentation, we saw that when we compute the pseudo inverse, we have our design matrix X, and then we take our design matrix X and we compute X transpose, right? And then we compute this product X transpose X, take the inverse, and we multiply that, left multiply that times the X transpose. So we need that X transpose. Okay, so going back to Matlab, we have our X transpose. Well, Matlab notation is just X apostrophe, or tick mark if you call it that. So we have our X, we compute our X transpose. So if we look at the dimensions, let's go ahead and do that. We look at the dimensions of X, that's 100 examples by 2 columns, right? So it's 100 by 2. We started out with 100 by 1, or 100 by D, where D is equal to 1 because it's one-dimensional for original data, and we augmented it with an X naught. So you can see here for the first row of this X matrix, or design matrix, we have the X naught, and then we have that feature, which is 250, right? So row by row represents an augmented vector. Okay, so we compute X transpose, and here we have a row matrix. If we take X transpose, it's now a column matrix. Right, so here, the first column, we can see the 1, and then we can see the 250. So instead of row, we have column matrix, and we have our X, and we have our X transpose. So we have everything we need for the beginnings of the pseudo inverse. So now we're going to compute X transpose X. Well, that's just the matrix product. So we take X transpose, we multiply it by X. So there's our X transpose X. All right, so we compute our X transpose X, and now because X transpose is 2 by 100, X is 100 by 2, the resulting X transpose X is going to be 2 by 2, because the result of the matrix multiplication is the outer set of dimensions. That would be 2 by 2. So if we look at X transpose X, that's 2 by 2, and that's our result for X transpose X. Okay, so now we're going to compute the inverse of X transpose X, and we're going to left multiply that by X transpose. And that's going to build us our pseudo inverse, and we're going to call that XP-inv for the pseudo inverse of design matrix X. So here we have X transpose X. We're going to take the inverse of that. That's this part of the statement, and then we're going to multiply that by X transpose, and that's our result, and our result is the pseudo inverse. Now that will absolutely work, but in Matlab there's a more efficient way to do that. The efficient way to do that is, instead of left multiplying by the inverse of X transpose X, you do this division. That's called a right-hand division. Whenever you multiply by the inverse, that's the same as dividing. And this backslash in matrix notation in Matlab is the right-hand division, so to speak. And this gives you this better result. It's more efficient computationally within Matlab internals, different set of algorithms they use. But they're both equally valid, so I'll leave this commented out, and I'll use the inverse version and leave it up to you to tinker with other versions of the inverse. Okay, so we compute this inverse step, and we notice here this inverse is 2 by 100. So the X transpose X is 2 by 2. The X transpose is 2 by 100, so the resulting dimension is 2 by 100. So we take this 2 by 100 pseudo inverse, and we're going to multiply that by Y, and Y is 100 by 1. Right, so this results in a 2 by 1 result, and that's exactly what our W is. So we step through that, and now let's take a look at what this W is, right? So W is of rank 2, right? And these are our W vectors. The first position is W naught, and the second position is W1, right? And so we can actually draw what this regression line looks like. That's our solution to regression, which is a pseudo inverse of design matrix X times Y, which is exactly what we talked about in the theoretical description, the mathematical derivation. Okay, so let's step through this and let's plot what this looks like. So we'll bring back our figure, and these are our original data points that we read in from historical data. And so we'll keep that graph, and then we'll set a bunch of sample points along the x-axis, and these are going to be example annual salaries. And then we're going to compute what this regression line outputs for each one of those examples, just for the sake of plotting. And then we go ahead and we'll plot it. We'll do that in magenta, a little bit thicker line. And you can see this is exactly what that regression line is. And if you look at it, well, it's in the middle of all of the data. Okay, so now what I'm going to try is using this to do prediction. So that W is the middle line, and now a new applicant comes along, and he or she inputs their annual salary, and this thing will now use this regression line to output what the appropriate line of credit amount should be. So we do this. Let me continue, and I'll uniformly at random sample from the salary interval from 1 to 100,000 on the real number line, and then I will call this predict mortgage, and predict mortgage just uses this linear weight and computes W0 X naught plus W1 X1 and uses that linear best model, that best line, the final best hypothesis, to output a real valued quantity, which is the recommended line of credit. Okay, so let's do that. Let me continue, and I loop through and print it out. And so here, if your salary, someone comes along with $79,428.66, a big old bank, fictitious bank, I won't mention any particular bank, says that you should get $465,287.55. I love the cents part for the mortgage. And I say mortgage, I really mean to say line of credit. Let me change that to line of credit. I'm so used to saying mortgage. So let's save that and let's rerun it. Let's continue. Let's do that again. Let me just start out by clear, CLC. Let me keep that figure. Continue. And here we go. So there's our regression line. And it says for a salary of $8,083.05, your line of credit will be $119,000. Wow. So $22,898. Line of credit is $189. For salary of $91,333, that's $523. For $15,000 and change, it's $152. And for $82,000 roughly of salary, it's outputting that you should be getting a line of credit $480,000. So with that, this is our demonstration of regression, and what we've done is implemented all of the mathematics over which we've done derivation previously. We've taken a data set, which are these points that we've plotted. We calculated the regression line using the pseudo inverse, and then we've taken that regression line to predict or output real valued labels associated with brand new salaries that we input here and selected uniformly at random. Okay, so let's go back to PowerPoint and finish up. And so that was our Matlab description, our Matlab implementation of this regression algorithm. It's pretty simple. You can do it in polynomial time. The biggest portion of it is constructing this design matrix and computing the pseudo inverse. And so with that, we'll end there. This ends our demonstration of linear regression, and what lies on the road ahead on Thursday, our final module for the semester. We will have a brief, very brief refresher on clustering, and then we will talk about the final project, which will be your final exam, which will be an image clustering experiment. So I will see you on Thursday.